Alright, on to question Mickey. 20 points. We're going to consider lithium plus. So we have 2 electrons in a triply charged lithium nucleus. So Mickey 1 for 5 points. How does the Schrodinger equation change compared with lithium double plus? What's the biggest complication in this and why? So we have 2 electrons now, not 1 electron, and it's probably going to have something to do with that. Now the potential changing is always, the Schrodinger equation changing is always the potential. The only thing that ever changes is the potential. So the potential now has 3 terms, a minus 3 over r1, a minus 3 over r2, and a plus 1 over the distance r12 between the 2 electrons, all multiplied by the appropriate factor, which is about 2 Rydbergs. So the change is the addition of the second attractive term and very much the addition of the repulsive term between the electrons, and that is the problem. The repulsion term is the biggest complication, and the reason is because it couples the 2 electrons. So when we've coupled the 2 electrons with the repulsion of the electrons, this introduces what we call electron correlation, and it also kills the separability. We can't just say it's the product of 2 wave functions anymore. We don't have the separation of variables in that aspect of the wave function. That makes the math much harder. Okay? That's that. Now, the next one is for 8 points. Sound like a game show host here. For 8 points, we have the ground state for lithium plus is a 1s2 configuration. The term is singlet S0. What are the configurations and term symbols for the first 3 higher energy terms, including the spin orbit states for each term? So, just to point it out, in 1s2 singlet S0, that's a configuration term and level. The configuration is 1s2, the term symbol is singlet S, and then the spin orbit level is that subscript 0. I need the next 3 term symbols with configurations and spin orbit terms. You need to specify the order of energy and defend your ordering, and you must include in your discussion the radial wave functions and the electron exchange symmetry. Alright, well, I basically have 1s, 2s, and 2p orbitals available for my 2 electrons. We've already dealt with the 1s being filled, so it's that 2s and 2p that's got to be in play. So for starters, why don't we put an electron in the 1s and an electron in the 2s? This gives an A state with a configuration 1s1, 2s1, and I'm going to align the spins to make that a triplet S1. It's a triplet because the total spin is 1 with the spins aligned, so that's G of S is 3, S because there's no orbital angular momentum, and the total J value is L plus S. L is 0, S is 1, and so that's going to be 1. So triplet S1 is the lowest energy case. Next, I'm going to flip that 1 electron so it's anti-aligned, and we're going to make ourselves a B state, which is the same configuration, 1s1, 2s1, but now it's a singlet S0. Singlet because the spin is 0, G of S is 1, L is still 0, so we have no spin, no orbital angular momentum, so the J spin orbit level has to be 0. And then finally, we're going to take that electron and do the next thing we can possibly do with it, which is promote it into the 2p, and that gives us a C, 1s1, 2p1. So now L is 1, and we're going to align the spins for a spin of 1, so we have spin and orbit of 1 each. This gives us a triplet P, and we have 3 options for the total J value. It can be 0, 1, or 2 because we can take the 1 of spin and the 1 of orbit, subtract them, add them, or kind of diddle around and do nothing. So 0, 1, and 2 are all possible, and those are the 3 next highest energy term symbols with spin orbit levels designated. Okay, I know we did 0, 1, 2 in that case because we're less than half full. So that's the answer to the question, and they're ordered by ABC. The question is why? There's increasing energy. So first we got the A and the B symbols, the term symbols. They have the exact same configuration, so they have the same general spatial wave function, but the triplet S has a symmetrical spin exchange wave function, which means it has to have an anti-symmetrical spatial exchange wave function, and that's going to make it lower in energy because the anti-symmetrical spatial exchange wave function has lower kinetic energy because it doesn't have a cusp, and thus it's basically easier to keep the electrons apart from each other. A lot of people just sort of said that higher spin is lower in energy. That's true, but I need an explanation for why to get full credit on this question. So now we have the triplet P012K. So here's what those wave functions look like for full credit. There's the antisymmetrical one. We have lower curvature at the R12 equals 0 case. Now for the triplet P012, the 2p orbital has no chance of getting very close to the electron, where the 2s orbital has a secondary maximum near the nucleus. So that's roughly what the probability distribution for 2s looks like, with a secondary maximum. Here's the 2p, no secondary maximum. So the 2p electron is shielded with respect to the 2s electron, and that makes for higher in energy. So that shielding is why p orbitals have higher energy than s orbitals with the same principal quantum number. Now here, the two key elements are, first of all, having the triplet and not the singlet, because for the same reason that the triplet is always lower in energy. Secondly, don't promote that electron out of 1s. The 2s and 2p energy levels are very, very close to each other compared to the enormous difference between 1s and 2s. So you can't promote out of the 1s after getting one electron out. Just a question of where we're putting that promoted electron. Leave a single electron down in the 1s orbital. There were some number of errors there. Not specifying the shielding term certainly is a problem. Finally, just worth pointing out, if you look this up in reality, it turns out that the actual spin orbit states are 0, 2, 1, 2, and 0. So 0 actually winds up being the highest energy of all, and that just points out that Hund's rules don't actually hold all the time for excited states. So you actually have to look them up. But if we followed our rules, it would be triplet P012. Reality is a little more complicated. Things have a way of being a little surprising sometimes. All right, part 3 for 7 points. Now, we can write the 2-electron spatial wave function of the 1s2 singlet S0 term that we just did as 1s1 2s2. I want you to write the properly symmetrized 2-electron wave function for a 1s1 3p1 configuration. So 1s1 1s2 is properly symmetrized because I exchange 1s1 and 1s2, and I have 1s1 and 1s2. We want the properly symmetrized 2-electron wave functions for 1s1 3p1 configuration. We have to address both the spatial and the spin parts of the wave function, where spin is represented as alpha and beta. Don't worry about the normalization, and then I want you to defend why 1 is lower in energy. So, first of all, there's wave functions here. So, these are both triplet P. There's going to be a 1s1 3p2 minus 1s2 3p1. So that is symmetrizing the spatial part, and that's anti-symmetrical. So the symmetrical spin exchange wave functions are alpha 1 alpha 2, alpha 1 beta 2 plus alpha 2 beta 1, and then beta 1 beta 2. Think up and down, but in the same general direction, and down down if you want. So those are 3 spin wave functions which are all symmetrical with respect to exchange. Those 3 spin wave functions are the triplet. That's why it's a spin triplet with a spin degeneracy of 3. The other possibility is to make the spatial exchange wave function symmetrical, 1s1 2p 3p2 plus 1s2 3p1, and then we make the spin anti-symmetrical, which we can only do one way, alpha 1 beta 2 minus alpha 2 beta 1, with the spins perfectly anti-correlated. There's just one of them, so it's singlet P. That one, the triplet, is lower in energy for the reasons that we also had in the previous question. It's lower energy because the curvature, the del squared, has lower kinetic energy near R12 equals 0, where the electrons are avoiding each other because it doesn't have any curvature. Whereas with the singlet P, the singlet symmetrical spatial exchange wave function has higher energy because of that cusp and high curvature.